Hi, my name is Anwar Sultan and I'm going to present some of the new ideas on gas chromatography, site maintenance and monitoring that we have. The objective of the presentation today is first to review the current gas chromatography maintenance regime that people have. And then from there, we'll have a look at the possible improvements, the GC maintenance and monitoring. To begin with, we'll start with the current maintenance regime. One of the first things that people do on the GC maintenance is repeatability tests. And this repeatability test here in the UK is normally based on the ASTM D1945 standard as a repeatability tolerance. It's normally done between 2 to 5 runs. And the reason for that, there's only sometimes people only do it only 2 times, is because a lot of typing involved in it. So it's quite prone as well to human error in typing. Now, one of the things about repeatability tests, what I think is really useful, because repeatability tests on the modern GC very, very seldom fails. It almost always passes. The reason I'm saying that is because of this particular example. Consider that we have 5 rounds of repeatability tests done on the GC. This is a result from the actual GC. If you can see, the blue line is the actual measurement of the methane, and the yellow line is the calibration gas value of the methane. And this bit is actually the tolerance of the ASTM D1945 standard. You can actually see from here that the result is so much better than the actual tolerance. If we extend the repeatability test into 40 hours test, the result is pretty similar. The result still within the tolerance limit, and it's well within the tolerance limit. And it doesn't only happen for methane only, it also happens for every other gases such as propane, butane, and every other gases in the system. So my question is it really worth doing? Because the GC can actually perform so much better than the actual tolerance that we've been using. How can it go wrong in terms of repeatability tests? There's a few things can go wrong. First thing is, like, if we actually use the wrong procedure, it actually leads to false impression. Here's an example. People start using the unnormalized value to compare it against the certified standard. And when the unnormalized total is high, it will give us quite a high reading. If the unnormalized total is low, it will give us quite a low reading. And sometimes the repeatability test fails because of that. And it basically leads to a false impression that the GC isn't working properly, that it's not repeatable enough. The other thing is that false impression that pass means accurate. So people start doing repeatability tests and it always passes. So they think my GC must be right because it always passes repeatability tests. Actually, if it's configured wrongly, it can actually be repeatedly wrong, because GC is quite a dumb device. It's only as good as how we configure it. So repeatable result doesn't really mean accurate. Repeatable means that the GC can perform well or measure the same thing in the repeatable manner. So the other thing that people do is control chart. It's basically just a plot of response factor and retention time of the GC. So what's the control limit on the control chart? What people have been using as the limits for the control chart is sometimes 3 standard deviation of first 25 data, sometimes 3 standard deviation of all data is set as a control limit. Is this right? Because what if GC has been performing well from the beginning, which means we will have a small standard deviation. So what if GC have been performing poorly from the beginning? That means we have big standard deviation. What this means is that the GC that has been performing well from the beginning is prone to control chart failures because we have a small standard deviation. And when the GC has been performing poorly, we have quite a big standard deviation and always pass. It's just not right limit. This is just basically one of the points that I would like to make about the control chart and about the limit, how we actually use the limit nowadays. To prove a point, consider this theoretical values. There's two charts here that have the same exact standard deviation of 3%. Basically, the current practice say that both GC works equally good. So if we see this chart here, the first chart we see is only on the methane, and now we actually put methane and nitrogen in the same trend. So the first trend, we actually see a synchronous change on methane and nitrogen varies in the same exact synchronous manner, while the second chart, methane and nitrogen, varies in very random manner. If we look at this individually, we can actually see that both of them having 3% standard deviation, which is okay. So from here alone, we see that the GC is working properly. Then if we put more gases, in this example, we got only 4 gases, you can actually see visually that the first chart is actually GC that performs better than the second chart. And then if we put every gases in the charts, then the first one is all synchronous, the second one is all random. We know exactly that the first one have a better performance than the second one. Now what that means, if everything is synchronized on the first chart, just talk about the first chart a little bit. If we treat the calibration points, the response factor of the calibration points as a mole percent rather than the response factor, we can actually convert them to mole percent and use the footprint as our reference. What that means is, let's say we have an 80% methane. If everything goes up and down synchronously, the normalized result of the mole percent throughout those charts, it will give us 80% of methane. That means it's always going to be constant. It's not going to be the same case on the second chart because of the random variation in the response factor. So now we know that visually that the first chart is better than the second chart. But how can we quantify? We can basically use the uncertainty analysis of the result. See the result here, we can actually see the CV uncertainty is all 0 on the first chart, and then it's quite high number on the second chart. We can also see the uncertainty of each component there is 0% on the first chart, and it's quite a high number on the second chart. And the reason for that is my original point, when we use a footprint as a reference, the normalized result of the synchronized chart will always be the same, while the normalized result of the random chart is more random. Now we can actually see an actual example of natural GC. So in this example here is actually an example of a healthy GC control chart. What we see here is that if you use the current method with the limit of a 3 standard deviation, this GC will have failed. So we can actually see that the GC start deviates and it goes beyond the standard deviation limit. So current practice will say that the GC have failed. But if you actually look everything in harmony, everything all together as a whole, actually see everything goes up and down in harmony. We do have slightly worse hexane and heptane response factor than the rest. But it doesn't really mean that the GC is bad. What it means is that heptane and hexane will have less uncertainty value, or sorry, high uncertainty value than the rest of the component. You can actually see here is the result of the GC uncertainty calculation. You can actually see the value of the CV uncertainty, which is quite low, and then we can actually set the limit of the uncertainty value of the CV so that it will generate as an alarm in case the uncertainty goes beyond that. We'll also be able to see that the hexane and heptane performance is captured here as well. We can actually see that the uncertainty of hexane and heptane is much, much bigger than the rest of the component. Now, this brings me to a point. The first one is basically there's no standardized limit for control chart monitoring. The 3 standard deviation limit for each individual component doesn't really work because all the gases inside the GC is correlated, so we can't really monitor and decide if the GC works properly or not based on one component. That's basically my second point. The performance of individual component in the control chart cannot be used to determine the actual performance of the GC. Again, this is because of every gases is correlated in the GC, and depending on the unnormalized result of the total, everything can go up together or down together, so therefore everything needs to be seen as a whole. The last bit is basically the CV uncertainty can be derived or other uncertainty can be derived, and this uncertainty value may be a better performance benchmark for representation of the actual GC performance. We can actually see based on the uncertainty value if the GC is working well or not. So this current GC maintenance regime that we have with the GC repeatability test and the control chart doesn't really give us a lot of information on how to check the calibration gas correctness. People do have a method on how to check that the calibration gas is correct or not. What people normally do is when they change the calibration gas, they actually treat the calibration gas as test gas, as a sample gas, and they check whether the result of the analysis is similar to the calibration certificate or not. One of the issues is that people don't really know what to do if it doesn't, and what would be the actual difference to be used as a limit again. One of the scenario here that we have is that in the UK, in the North Sea, sometimes calibration gas is stored in the winter cold below the dew point temperature. What that means is that the heavy ends of the gas component will migrate to the bottom of the bottle, and it results in a non-homogeneous mixture. A lot of times, the technician will just believe what the certificate say. The certificate will be right because it should be. But if we actually have the bottle sitting cold in the winter cold, then the certificate will not represent what we actually have inside the bottle anymore. And a lot of times, this is what can happen. And what people are doing as well is that if they see something wrong, they sometimes do it again and again and again to see the repeatability of it. If it's repeatable, it must be right, although it's actually wrong. And this can actually lead to something like this. As you can see in the chart, the red chart is actually the actual one, and the green one is actually what should happen. And this thing here can actually lead to quite a significant measurement error. The other scenario is that people forget. It's a procedural issue that people don't really follow. This is an actual case from the North Sea, actually. A technician put a new cal gas and forgot to put the new component data table based on the new cal gas in the system. The thing that he forgot is he forgot to put a note that new calibration gas has been installed. So a few months later, the next technician came in. He wanted to start up the GC. But he found an error. The response factor is coming out with quite a big deviation. So he did it again, and it still have the similar big deviation on it. So what he did was he force calibrate the GC, and the result is something like that. And what we would expect from a response factor trend is that everything should be ascending. And this chart is nothing like what a control chart, what a response factor trend should look like. Based on this response factor trend, on this particular case study, the error actually amounts to around £300,000 a month when we use production of 100 million scarf per day. It's quite a significant error for a GC. And the biggest issue is because although they have the 2GC, because the problem is not on the GC, the problem is actually forgetting to put the component data table is the calibration gas. Both GC actually measuring the same exact result. So it's a systematic error that happened in dual redundant GC that people get to miss. So the other thing that people do is actually to compare the unnormalized composition between 2GC. And in many places, it's actually a contractual requirement to have a tolerance limit set between each of the component of the 2GC that measuring the same gas. And because of the wrong procedure, when you actually compare the unnormalized value, it can actually lead to a wrong impression. Like in this case, it's actually the same exact gas. You see that when we have a normalized composition compared between the 2GC, the result fails. When we normalize it, actually the result is all good, because the difference is actually zero, because it's actually the same gas in this particular example. So all this stuff is basically led us to not enough confidence in our GC measurement. And one of the example of that is sometimes when the gas goes off spec and the GC reads that the gas is off spec, what gets the blame is normally the GC rather than the process gas. So, and a lot of times the technician with lack of competency, they just get panic. What's wrong with my GC? Where in fact the problem is not in the GC. There's a possibility that the issue is actually with the actual gas that is actually off spec. So we need all this tool to actually make sure that the technician know that the GC is actually working properly. This is basically all the new ideas that I'm going to put into place to tackle this issue and improve our confidence. So how do we do it? So the first thing in the idea is basically to have an automated system. This can be in the form of a diagnostic PC, a laptop, an HMI, basically anything that connects to the GC 24/7. Now, the advantage of an automated system is that it takes away the requirement of manual data entry to spreadsheet. It takes away the requirement of operators really doing excessive stuff in the GC. It basically removes the error from the operator, and therefore it saves a lot of hours of technician time just by having an automated system. And the other thing that is good about the automated system is that if the technician need to spend time on the GC, they will spend the time to interpret the data rather than entering the data into a spreadsheet. The other advantage of the automated system is that we can actually flag an alarm automatically in case one of the parameters fail. And then also we have all the historical data in our fingertips, because every single data is actually saved in the database. So once we have an automated system, we do check the log chart. The log chart is a check that we use to actually check whether calibration gas is correct or whether there's any valve timing issue. I just want to show you here that the current practices of what people do is not actually exactly right. In this particular case, this is a log-log chart of a GC that has a dual column on the valve. So basically, there's a change in the path. That means there's a change in the flow rate on the GC when the valve free is on and when valve free is off. What this means is that when that happens, the property of the thermal conductivity detector shift by a little bit. So what we need to do is, rather than looking at all the gases in the same chart, we need to separate them into two different charts. One of them that is measured when the valve free is on, and the other one is the one that's measured when the valve free off. So this chart here, as we see it, is not really necessarily mean that the GC is unhealthy, although the correlation failed. In fact, when separated into the two components, one of them is the one that's measured when the valve free on, and the other one is measured when the valve free off, all of the correlation is showing a very, very high correlation, which means that the GC is good. Now, what we can determine from the log-log chart first is that we can determine if the valve timing is right or wrong. And then the second thing is the calibration gas composition is as per the certificate. Why can we do that with the log-log chart is because the log-log chart is actually a physical representation of the actual physical property. The physical property of the gas doesn't lie. Each gases have a different thermal conductivity property. So when all the saturated gas that have exposed to the thermal conductivity detector in the same pressure, temperature, flow rate condition will have quite high correlation between them, and that's pretty much the concept. And if we have a low correlation, one of them will be wrong. Either the valve timing will be wrong, or the calibration gas composition is not as per the certificate that we have. Now, this will basically provide us with confidence that GC functioned correctly on that particular moment. Now, we know that GC works fine now. What do we do next? So once we have the confidence in the GC, we basically monitor the calibration result throughout the time to see whether the GC maintains its reproducibility. Now, how to do that is, rather than doing it with the control chart, we actually use similar thing as the control chart, but we actually derive the data from it to work out the uncertainty value of the GC. Now, the difference between this method and the control chart method is because we actually look at all the data as a whole rather than individually. This uncertainty value is derived from the whole data. So like, all the correlation is considered inside the GC. Once we derive the uncertainty value, we can actually get individual data of the uncertainty, like we can get today's uncertainty, tomorrow's uncertainty, yesterday's uncertainty, and then all the historical data of uncertainty can be trended, and we can actually see how the GC has been performing throughout time. Now, one of the things that I'd like to say about it is that GC is a very, very repeatable device. So what we want to do is we want to check a long-term uncertainty of the GC and also a short-term uncertainty of the GC. Now, consider this. If we have like a year worth of data and the GC has been good for a year, and then after a year it starts drifting, so the 7 days after a year the GC starts drifting, and we know the GC is going to fail soon. But when we see the whole year data, the 7 data that is bad is actually going to be covered by the 365 data that is good. So we can still see that the uncertainty will still be a low value of uncertainty. So what we suggest, if we actually take the last 30 days of uncertainty as well, so we can actually see the drift start going up. Because the 7 data is quite significant when we only see 30 days of data. So we can actually see both long-term and short-term uncertainty. So if the short-term uncertainty start to creep up, and then it will hit the limit, then it will generate an alarm, so we can decide to do a maintenance on the GC based on that particular alarm. So this is an example of the actual GC that we have of the uncertainty value. You can actually see that rather than 30 days data here, we actually just use 30 data because it's because of the limitation on time of the test. We just take more data in the more calibration on every day to show how the uncertainty works. So what we have here on the scale as well, if you see the scale is actually a very, very low scale. And this is just to show that we can see the long-term uncertainty, which is the dark blue line, and the short-term uncertainty, which is the light blue line. You can actually see that it shows a slight different thing. But if we actually see the actual limit, we can put a limit of 0.12%. You can actually see that the GC is actually performing way, way better than the limit that we have. But this is what we actually monitor. If we actually see that the uncertainty values start to creep up and getting close to 0.12%, then we know something's going to happen with the GC soon enough. The other thing that we want to check or suggest to check on the automated system is the last update of the calibration data. So automated system means like we have an auto calibration system. Let's say we have a 24 hours calibration that is automated in the GC. So what we expect, what the system expects, is the new data will be updated after 24 hours. So what we set up is that if after 24 hours there's no data, there are two possibilities. The first possibility is that maybe the GC calibration has failed. So there's some error suddenly happened in the GC that it doesn't update the response factor, or the response factor deviation is more than the limit that is set in the GC. The thing that might happen is that there might be a communication failure in the system. So which both of them can be easily checked. Now, if we have all this data and it's all automated, the only thing that the technician need to do on a daily basis is to see on the traffic light system. So we can put a traffic light system green for good or red for bad. So we base this data on the correlation. The correlation value need to be high, the uncertainty value need to be low, and the last calibration data need to be less than the set value, set periodic value. So based on this, if something goes wrong, we can actually tell what's actually causing the issue, and we can use the troubleshooting or the diagnostic tool to actually help us determine what's wrong with the GC. So how about control chart then? Are we still going to be using the control chart? Because sometimes it's a contractual requirement and people are wanting to fulfill that requirement of the contractual. So it's still there basically. We still be able to see all the control chart. We can still be able to see the standard deviation of them, but we can actually see them all in harmony now. And then we basically can interpret the data better because of the system that we have with this. The last thing that I want to say is that on the new thing, it's not really a new thing, it's probably just a reminder that we need to save the analysis parameter. So the analysis parameter is basically the parameters that we take, the GC parameters that we take when the GC is healthy. So these are some of the parameters that we should take from the GC, like the GC oven temperature. Basically, the GC oven temperature on a healthy GC will be pretty much constant all the time. There's not going to be any change in the carrier gas pressure. There's not going to be any change in valve actuating pressure. Carrier gas flow rate needs to be measured through each path. So in some of the GC, like when valve 3 is on, it needs to be measured. When the valve 3 is off, it needs to be measured. Where we know that there's going to be a possible difference in the flow rate. So we write this down, and then if something goes wrong, we'll have a look at it. there's no way that the GC goes wrong and all these parameters will stay the same. One of these parameters will have changed if something goes wrong with the GC. So basically with this, it will help us, knowing all this information, it will help us pinpointing where the issue is with the GC in case of failures. So in conclusion, the current method of repeatability check and control chart, although it is a requirement, I find that it doesn't really give us too much of added value in terms of maintenance, and we can actually do so much better with using the uncertainty value rather than the repeatability check and the control chart. Well, I think here that we can actually remove repeatability check altogether and use uncertainty value to determine the health of the GC. Now, why I say that? Because if we have a good GC with low uncertainty value from its daily calibration, it basically says that we have a good reproducibility in the GC. Now, when we do a reproducibility check, it's over a long period of time, and good reproducibility actually implies a good repeatability. If we can say that the GC has been reproducible for the last 6 months, for instance, theoretically it shouldn't fail when we test it for 20 minutes. On the new ideas, what I think is we can actually implement an automated system, and then we check the correlation value of gases that flows through the same path, and therefore we can make sure that all the valve timing is correct, the calibration gas is as per the calibration gas certificate, and then the next thing that we do is we monitor the GC performance based on the uncertainty value of the CEV, which can be calculated after every calibration. Now, this is basically will tell us how good the GC been performing throughout the year. The other thing that we need to monitor, because it's an automated system, is the last calibration date, just to make sure that there's no communication failure in there or no calibration failure in the system. Either way, we can actually check them both. Alarms, then we can set the alarms based on these 3 parameters. If the correlation is low, then we set the alarm. If the uncertainty value goes beyond the limit, we set an alarm. If there is no calibration, for instance, or no communication, it sets the alarm. So we can actually maintain the GC every day throughout the year. And therefore it basically confirms that the GC is healthy throughout the year. And in case it doesn't go healthy, in case something goes wrong, we know most of the time we can actually know before it actually goes really wrong, because normally GC drift rather than go into a failure abruptly. Last but not least, the healthy GC analysis parameter need to be safe, and this basically will help us pinpoint the issue when we troubleshoot a GC. Although some of the tools in terms of the new ideas will help us determine what's wrong with GC as well. Knowing the healthy parameter of the healthy value of the parameters will help us confirm our diagnostic as well. And that concludes my presentation. Thank you very much. If you have any question, you can send me an email at anwar.sultan@i-vigilant.com, or please visit our website at www.i-vigilant.co.uk, where you can download some of our papers over there as well. Thank you very much for listening. Bye-bye.